The recent earthquakes in the Sierra are a great reminder of California's other very active earthquake zone. Now, when you think about earthquakes, you're probably thinking about earthquakes along the San Andreas Fault.
A ticking time bomb lies hidden beneath California's surface, and NASA has just sounded the alarm. The space agency has detected a deeply concerning crack within the infamous San Andreas Fault, formed by the relentless grinding of tectonic plates. This hidden fracture is building up immense pressure, threatening to unleash a catastrophic earthquake that could devastate major cities and leave millions in ruins. Join us as we delve into NASA's findings about the San Andreas Fault Crack and why it has people concerned. The San Andreas Fault. Imagine a giant crack running over 800 miles through the heart of California. This is no ordinary fissure. It's a tectonic boundary where two massive plates, the Pacific and North American, meet and grind against each other. This crack, known as the San Andreas Fault, is a ticking time bomb that could unleash a catastrophic earthquake at any moment. The San Andreas Fault is one of the most significant geological features in North America. It stretches roughly 810 miles from Cape Mendocino in Northern California to the Salton Sea in the south. This fault line marks the boundary between the Pacific Plate and the North American Plate, two of the largest tectonic plates on Earth. The history of the San Andreas Fault is marked by destruction and upheaval. In 1906, a devastating earthquake with a magnitude of 7.8 struck San Francisco, causing widespread damage and claiming over 3,000 lives. The quake ruptured the northern segment of the fault, displacing the ground by up to 20 feet in some places. More recently, the 1989 Loma Prieta earthquake, with a magnitude of 6.9, rocked the Bay Area, collapsing a section of the Oakland-San Francisco Bay Bridge and causing 63 deaths. The San Andreas Fault has been a source of concern for decades, with scientists warning of the potential for a massive earthquake that could strike at any time. As the pressure continues to build along the fault line, the question is not if, but when the next big one will occur. NASA's alarming findings. A closer look. Recently, NASA made a startling announcement that sent shockwaves through the scientific community and beyond. Their report, which is based on data collected from a network of GPS stations and satellite imagery, paints a grim picture of the potential for a devastating earthquake in the near future. According to the report, the San Andreas Fault is experiencing a rapid accumulation of strain, with some areas of the fault showing a buildup of stress that is up to 10 times faster than previously thought. This buildup of stress is caused by the constant movement of the Pacific and North American plates, which are sliding past each other at a rate of about 2 inches per year. The implications of this rapid buildup of stress are dire. Scientists believe that the San Andreas Fault is capable of producing earthquakes with magnitudes of up to 8.2, which would be among the most powerful earthquakes ever recorded. An earthquake of this magnitude would cause widespread damage and loss of life, with the potential for catastrophic consequences in densely populated areas like Los Angeles and San Francisco. The NASA report also highlights the fact that the southern portion of the San Andreas Fault, which runs through the Coachella Valley and the Salton Sea, is particularly vulnerable to a major earthquake. This section of the fault has not experienced a major earthquake since 1680, and scientists believe that it is overdue for a rupture. A major earthquake along this section of the fault could cause extensive damage to the region's infrastructure, including highways, bridges, and water systems. One of the most alarming findings in the NASA report is the discovery of a new fault line parallel to the San Andreas Fault. This fault line, which has been dubbed the Salton Trough Fault, is located just a few miles east of the San Andreas Fault and is believed to be capable of producing earthquakes with magnitudes of up to 7.5. The discovery of this new fault line underscores the complexity and unpredictability of the seismic activity in the region. The NASA report has sent shockwaves through the scientific community and has raised concerns among government officials and emergency responders. The California Governor's Office of Emergency Services has already begun to review its earthquake preparedness plans in light of the new findings, and officials are urging residents to take steps to prepare for a major earthquake. The implications of a major earthquake along the San Andreas Fault are staggering. With millions of people living in proximity to the fault, including the densely populated cities of Los Angeles and San Francisco, the potential for widespread destruction and loss of life is immense. Roads, bridges, and buildings could crumble, while essential infrastructure like power grids and water systems could be severely damaged. The science behind the fault line. To comprehend the gravity of NASA's findings, it's crucial to understand the science behind the San Andreas Fault and the forces that drive its behavior. At its core, the fault is a result of the constant movement of tectonic plates, the massive slabs of rock that make up the Earth's outer layer. At its core, the San Andreas Fault is a boundary between two of the Earth's tectonic plates, the Pacific Plate and the North American Plate. These plates are massive slabs of rock that make up the Earth's outermost layer, known as the lithosphere. The Pacific Plate, which lies to the west of the fault, is slowly moving northward at a rate of about 2 inches per year, while the North American Plate, which lies to the east of the fault, is moving southward at a slightly slower rate. The movement of these plates is driven by the convection currents in the Earth's mantle, which is the layer of hot, semi-solid rock that lies beneath the lithosphere. As the mantle churns and circulates, it exerts pressure on the overlying plates, causing them to move and interact with one another. At the San Andreas Fault, the Pacific and North American plates are sliding past each other in a horizontal motion, known as a strike-slip fault. This means that the plates are moving laterally along the fault line, with the Pacific Plate moving northward and the North American Plate moving southward. Over time, this movement can cause a buildup of stress and strain along the fault line, as the plates become locked together and resist further movement. When the stress and strain along the fault line becomes too great, the rocks can suddenly slip and release pent-up energy in the form of an earthquake. This sudden release of energy can cause the ground to shake violently, with the strength and duration of the shaking depending on the magnitude of the earthquake and the distance from the epicenter. The science behind the San Andreas Fault is complex and multifaceted, involving a wide range of geological processes and phenomena. Scientists use a variety of tools and techniques to study the fault, including seismometers, which measure the strength and direction of seismic waves, and GPS stations, which track the movement of the Earth's surface over time. One of the key challenges in studying the San Andreas Fault is the fact that it is not a single, continuous fault line, but rather a complex network of smaller faults and fractures that interact with one another in complex ways. This complexity makes it difficult to predict exactly when and where the next major earthquake will occur, and requires scientists to use advanced modeling and simulation techniques to better understand the behavior of the fault. Despite the challenges, scientists have made significant progress in understanding the San Andreas Fault and the seismic activity that it generates. They have identified patterns and trends in the frequency and magnitude of earthquakes along the fault line, and have developed sophisticated models to predict the likelihood of future seismic events. One of the most important findings in recent years has been the discovery of the seismic gap along the southern portion of the San Andreas Fault. This gap, which stretches from the Salton Sea to the Mexican border, has not experienced a major earthquake in over 300 years, leading scientists to believe that it is overdue for a significant seismic event. The complexity of the fault system. While the San Andreas Fault is often portrayed as a single, linear feature, the reality is far more complex. The fault is just one part of an intricate network of interconnected faults and fractures that crisscross California and beyond. The San Andreas Fault system is composed of numerous segments, each with its own unique characteristics and seismic history. The fault is divided into 3 main sections: the northern, central, and southern segments. Each of these segments is capable of producing significant earthquakes, but they behave differently and have distinct patterns of seismic activity. In addition to the main fault line, there are countless smaller faults and fractures that branch off from or run parallel to the San Andreas. These secondary faults, such as the Hayward Fault in the San Francisco Bay Area and the San Jacinto Fault in Southern California, can also generate powerful earthquakes and contribute to the overall seismic hazard in the region. The complexity of the San Andreas Fault system is further compounded by its interaction with other geologic processes. For example, the fault is influenced by the movement of tectonic plates, the effects of erosion and deposition, and even the weight of water in nearby reservoirs. These factors can alter the stress distribution along the fault, potentially triggering or delaying seismic events. Tectonic forces driving California's seismic activity. Beneath California's picturesque landscapes and bustling cities lies a relentless force that shapes the state's seismic destiny. The tectonic plates that make up the Earth's crust are in constant motion, and California finds itself at the mercy of two major players: the Pacific Plate and the North American Plate. Imagine a slow-motion collision of titans, with the Pacific Plate grinding relentlessly against the North American Plate. This battle of geological behemoths is the primary driver of California's seismic activity, with the San Andreas Fault serving as the front line. The Pacific Plate, which includes much of the ocean floor west of the Americas, is slowly inching its way northwest at a rate of about 2 inches per year, relative to the North American Plate. As these plates move past each other, they don't do so smoothly. Like two giant hands grasping each other, the plates can become locked together, causing stress to accumulate along the fault lines. This stress builds up over time, storing immense amounts of energy in the Earth's crust. The rock bends and compresses like a giant spring being wound tighter and tighter. Eventually, the accumulated stress becomes too great for the fault to withstand. In a sudden and violent release, the plates slip past each other, generating powerful seismic waves that radiate outward from the fault. This is the moment an earthquake is born, unleashing its destructive energy upon the surface above. Monitoring and mitigating earthquake risks in California. In the face of the ever-present seismic threat, California has become a hub of earthquake monitoring and mitigation efforts. At the forefront of this endeavor is the United States Geological Survey (USGS), a scientific agency dedicated to understanding the Earth's processes and minimizing the risks posed by natural hazards. The USGS operates a vast network of seismometers and monitoring stations throughout California, constantly listening for the telltale signs of seismic activity. These sensitive instruments can detect even the faintest tremors, providing scientists with a real-time picture of the state's seismic landscape. The data collected by these devices is crucial for understanding the behavior of faults, tracking earthquake patterns, and ultimately improving our ability to forecast future seismic events. One of the key tools in the USGS's arsenal is the Shake Alert system, an earthquake early warning network that aims to provide crucial seconds to minutes of warning before the shaking begins. By detecting the initial P waves generated by an earthquake, which travel faster than the more destructive S waves, Shake Alert can rapidly calculate the location, magnitude, and expected shaking intensity of the impending quake. This information is then transmitted to smartphones, computer systems, and infrastructure networks, allowing people and automated systems to take protective actions before the shaking arrives. In addition to monitoring and early warning, the USGS plays a vital role in assessing seismic hazards and guiding risk mitigation efforts. By studying past earthquakes, analyzing fault behavior, and creating detailed seismic hazard maps, scientists can identify areas of heightened risk and inform land use planning, building codes, and emergency response strategies. This knowledge is essential for helping communities make informed decisions about where to build, how to design resilient structures, and how to prepare for the inevitable earthquakes that will strike in the future. The potential role of dried-up lakes. While tectonic forces are the primary drivers of seismic activity in California, recent research has shed light on a surprising potential contributor to earthquake risk: dried-up lakes. These ephemeral bodies of water, known as playa lakes, have been proposed to influence fault behavior in ways that scientists are only beginning to understand. Imagine a vast, shallow lake, its waters glistening under the California sun. Over time, as the climate changes and water resources are depleted, the lake begins to shrink, its edges receding until all that remains is a parched, cracked expanse of land. This is the story of many of California's playa lakes, which have disappeared or drastically diminished in recent decades. But what does the fate of these lakes have to do with earthquakes? The answer lies in the complex interplay between water, rock, and the immense pressures that exist deep within the Earth's crust. As playa lakes dry up, the weight of the water that once filled them is removed, potentially altering the stress dynamics of nearby faults. One hypothesis suggests that the presence of water in the pores and fractures of the rocks surrounding faults can act as a lubricant, allowing the two sides of the fault to slide past each other more easily. As the water disappears, the friction between the rock faces increases, potentially leading to a buildup of stress and a heightened risk of earthquakes. Another theory proposes that the loss of water from playa lakes can cause changes in the pressure gradients within the Earth's crust. This pressure differential may alter the stress distribution along faults, potentially making them more susceptible to rupture. However, it's important to note that the influence of dried-up lakes on seismic activity is still a matter of ongoing research and debate. While these hypotheses offer intriguing possibilities, they must be considered in the context of the broader geological forces at play. Tectonic plate movement, the accumulation and release of stress along faults, and other factors like the Earth's internal heat and structure all contribute to the complex seismic landscape of California. Now it's time for today's subscriber pick. NASA warning: San Andreas Fault Crack on the brink of eruption. This chilling headline has sent shockwaves through California and beyond, as the media scrambles to relay urgent warnings and prepare the public for what could be the most devastating natural disaster in the state's history. Experts warn that a major earthquake could cause catastrophic destruction, potentially affecting millions in densely populated cities like Los Angeles and San Francisco. A magnitude 8 or higher earthquake could crumble buildings, bridges, and roads, while landslides and liquefaction could further compound the damage. The potential death toll is staggering, with thousands of lives at risk, and the economic impact would be immense. What are your thoughts on this impending crisis? Let us know in the comments. The significance of Lake Cahuilla. In the arid expanse of Southern California, the ghost of a lake holds the key to understanding the region's seismic past and future. Lake Cahuilla, a vast body of water that once covered much of what is now the Coachella and Imperial Valleys, has been the subject of intense scientific scrutiny in recent years, as researchers seek to unravel its potential influence on the southern San Andreas Fault. The Lake Cahuilla story is one of cycles and change. Fed by the mighty Colorado River, the lake would swell and recede over the centuries, its waters lapping at the edges of the surrounding mountains. As the lake filled, its immense weight would press down on the Earth's crust, altering the stress dynamics of the nearby faults. Recent studies have suggested that the filling and draining cycles of Lake Cahuilla may have played a critical role in regulating seismic activity along the southern San Andreas Fault. Researchers have found that major earthquakes in the region tend to coincide with periods when the lake is either full or in the process of filling. The idea is that the weight of the water in the lake acted as a sort of seismic safety valve, exerting pressure on the fault and preventing the buildup of excessive stress. As the lake filled, it would essentially pin the two sides of the fault together, making it more difficult for them to slip past each other and generate earthquakes. But as Lake Cahuilla began to disappear, drying up over the past 3 centuries due to a combination of climate change and human activity, this seismic safety valve was removed. The vanishing waters left behind a fault system that was primed for movement, with centuries of accumulated stress just waiting to be released. The gradual desiccation of Lake Cahuilla may have set the stage for a future earthquake of devastating proportions. As the lake's water receded, the pressure on the fault diminished, allowing the two sides to slowly inch past each other and accumulate strain. Like a rubber band being stretched to its breaking point, the southern San Andreas Fault may now be nearing a critical threshold, with the potential for a sudden and violent rupture. The seismic hazard posed by the southern San Andreas Fault. What makes the southern San Andreas Fault so dangerous is its proximity to some of the most densely populated areas in the United States. The fault runs directly through the Coachella Valley, home to over 500,000 people, and skirts the edges of the sprawling Los Angeles metropolitan area, where more than 18 million people live and work. If a major earthquake were to strike along this section of the fault, the consequences could be catastrophic. Imagine the ground shaking violently, buildings crumbling, and roads buckling as seismic waves rip through the Earth's crust. The damage would be immense, with the potential for thousands of casualties and billions of dollars in economic losses. Critical infrastructure, such as highways, bridges, and power grids, could be severely damaged or destroyed, hampering rescue efforts and prolonging the recovery process. But what are the odds of such a disaster? Scientists point to a chilling pattern. The longer the interval between major earthquakes on a fault, the greater the likelihood of a significant seismic event in the future. The southern San Andreas Fault has not experienced a large earthquake since 1857, when a magnitude 7.9 quake ruptured the fault from Parkfield to Wrightwood. That's over 150 years of accumulated stress, just waiting to be released. Seismologists warn that the southern San Andreas Fault is overdue for a major earthquake, with some estimates suggesting a 70% probability of a magnitude 7 or greater quake occurring within the next 30 years. The U.S. Geological Survey's shakeout scenario, which models a hypothetical magnitude 7.8 earthquake on the southern San Andreas Fault, paints a grim picture. Over 1,800 deaths, 50,000 injuries, and $200 billion in damage. Rehabilitating the Salton Sea, balancing environmental concerns and seismic risks. Recently, a vast saltwater lake in Southern California known as the Salton Sea has become a focal point of environmental and seismic concern. This accidental lake, created in the early 1900s when an irrigation canal burst and allowed the Colorado River to flow unchecked into the Salton Basin, has been slowly shrinking and becoming increasingly polluted in recent years. The receding waters of the Salton Sea have exposed vast expanses of lake beds, which dry out and release toxic dust into the air. This dust, laced with pesticides and heavy metals from agricultural runoff, poses a serious health risk to nearby communities, exacerbating respiratory problems and other illnesses. The shrinking lake also threatens the habitat of over 400 species of birds and other wildlife that depend on its ecosystem. In response to these pressing environmental concerns, various plans have been proposed to rehabilitate the Salton Sea. These efforts aim to stabilize the lake's water levels, control dust emissions, and restore critical habitats for fish and birds. One key strategy involves importing desalinated seawater from the Gulf of California to replenish the lake and maintain a stable shoreline. However, recent research has added a new layer of complexity to the Salton Sea rehabilitation efforts. Scientists have discovered a potential link between the lake's water levels and seismic activity along the nearby San Andreas Fault. The southern San Andreas Fault, which runs along the eastern shore of the Salton Sea, is considered one of the most dangerous fault segments in the United States. Studies suggest that significant changes in the water level of the Salton Sea could potentially trigger seismic activity along the fault. As the lake's water recedes, it removes a significant weight from the Earth's crust, which may alter the stress distribution along the fault and increase the likelihood of an earthquake. This seismic risk must be carefully considered in any efforts to rehabilitate the Salton Sea. Balancing the urgent need to address environmental and public health concerns with the potential seismic consequences of altering the lake's water levels is a delicate and complex task. The historical context of major earthquakes in California. Over the centuries, California has been rocked by numerous major earthquakes, each one leaving an indelible mark on the landscape and the lives of those who experienced it. One of the most devastating earthquakes in California's history occurred on April 18, 1906, when a massive magnitude 7.8 quake struck the San Francisco Bay Area. The earthquake and the subsequent fires that raged through the city claimed over 3,000 lives and left more than 200,000 people homeless. The 1906 quake remains a powerful reminder of the destructive potential of seismic activity along the San Andreas Fault. Nearly a century later, on January 17, 1994, the Northridge earthquake shook the Los Angeles area with a magnitude of 6.7. Despite its relatively moderate size, the Northridge quake caused widespread damage, with over 50 deaths, thousands of injuries, and an estimated $30 billion in economic losses. The Northridge earthquake highlighted the vulnerability of urban areas to seismic hazards and spurred efforts to improve building codes and retrofit existing structures. These historical earthquakes, and the many others that have occurred throughout California's history, offer valuable lessons for seismic risk assessment and preparedness efforts. By studying the ground motions, damage patterns, and societal impacts of past events, scientists and emergency managers can develop more accurate models of potential future earthquakes and their consequences. One key insight from California's earthquake history is the importance of understanding the recurrence intervals of major seismic events. The 1906 San Francisco earthquake, for example, occurred after a period of relative seismic quiescence along the northern San Andreas Fault. The long interval between major earthquakes allowed stress to accumulate along the fault, ultimately leading to a more powerful and destructive event. Similarly, The southern San Andreas Fault has not experienced a major earthquake since 1857, raising concerns about the potential for a large-scale event in the near future. By examining the historical context of major earthquakes in California, we can better appreciate the cyclical nature of seismic activity and the importance of preparing for the inevitable. Another critical lesson from California's earthquake history is the need for robust building codes and infrastructure design. The 1933 Long Beach earthquake, which caused extensive damage to unreinforced masonry buildings and schools, led to the adoption of stricter building codes and the retrofitting of vulnerable structures. These efforts have undoubtedly saved countless lives in subsequent earthquakes. Preparing for the inevitable, mitigating the impact of a major earthquake. In the face of California's ever-present seismic threat, preparedness is not a luxury, but a necessity. As scientists warn of the growing likelihood of a major earthquake striking the state in the coming years, it is crucial that communities, businesses, and individuals take proactive measures to mitigate the potential impact of such an event. Earthquake preparedness begins with knowledge and awareness. By understanding the seismic hazards facing their region, Californians can make informed decisions about how to protect themselves, their families, and their property. This includes learning about the location and behavior of nearby faults, the potential intensity of ground shaking, and the secondary hazards that may accompany a major earthquake, such as liquefaction, landslides, and tsunamis. One of the most effective ways to reduce the risk of injury and property damage during an earthquake is to ensure that buildings and infrastructure are designed and constructed to withstand seismic forces. This involves the implementation of strict building codes, the retrofitting of older structures, and the use of innovative engineering techniques to enhance the resilience of critical facilities like hospitals, schools, and bridges. In recent years, advancements in seismic monitoring, modeling, and forecasting have greatly improved our ability to detect and characterize earthquakes in real time. The deployment of dense seismic networks, such as the USGS's Shake Alert system, allows for rapid detection of seismic waves and the issuance of early warning alerts to communities in the path of an impending quake. These precious seconds of advance notice can provide critical time for people to take cover, for trains to slow down, and for utilities to shut off gas lines, potentially saving lives and minimizing damage. Thanks for watching, and we'll see you in the next one.